In this video, I'm going to introduce the Black-Litterman asset allocation model. This model was developed by Fisher Black and Bob Litterman, who both worked for Goldman Sachs. It's called the Black-Litterman asset allocation model, but really it is a model to calculate expected excess returns. After we have calculated expected excess returns, we then use standard techniques to solve for the optimal portfolio, with or without short selling constraints. And we've done that in a previous video. The thing that is novel about the Black-Litterman model is that it allows investment managers to incorporate their views on stocks, industries, and/or countries. If you think back to what we used in the past to estimate expected excess returns, we either used the average historical return for a stock, or we used the CAPM to get an estimate of expected returns. That didn't allow us to incorporate our views about the performance of a stock. The Black-Litterman model does allow us to incorporate our views, and it's used a lot in practice. Many fund managers use the Black-Litterman model for their asset allocation strategies. To provide an overview, the Black-Litterman model essentially combines information from two sources to create an estimate of expected returns. The first source is, what does the current market tell us about the expected excess returns? This is the implied excess equilibrium returns that we calculated in the previous video. The second source is, what views does the investment manager have about particular stocks, sectors, asset classes, or countries? And the model combines these different sources to produce estimates of expected excess returns. Here is the formal equation for the Black-Litterman model. Expected excess returns are equal to the inverse of tau times by S plus P transpose times by omega inverse times by P, and all of that is then to the power minus 1, so it's the inverse, and that is multiplied by the inverse of tau times by S multiplied by pi plus P transpose times by omega inverse times by Q. Long formula, looks very complicated. What we're going to do in this class is simplify this formula. S is the variance-covariance matrix. We've seen that before. P is what we're going to call a link matrix. It's a matrix which identifies the assets about which we have views. Omega represents the uncertainty of our views about an asset. Pi represents the implied equilibrium excess returns. And Q represents our views. To understand this formula, we're going to split it into two sections. Section 1. Section 2. And we're actually going to start with the second part first. In this part of the formula, we're combining the implied equilibrium excess returns with our views on the implied equilibrium, with our views on the expected excess returns. Essentially, we're calculating a weighted average of the implied returns and our views. The question is, what are the weights? And the weights are how confident the investor is about his or her views relative to the confidence with which we estimate the implied excess returns. So the weights that we're looking at here, the inverse of tau S and P transpose times by omega inverse, These are measures of confidence. The more confident we are about our views relative to the implied excess returns, the more weight we will place on our views. That makes sense. That's what you would hope would happen. Suppose we are uncertain about the value of an analyst's prediction. How is this going to translate in our formula? It will mean that if there's a lot of uncertainty about an analyst's prediction, the elements of omega will be large to reflect that uncertainty. But if omega is large, the elements of omega inverse will be small. When we calculate the expected excess returns, that means the analyst's predictions will only make a very small contribution to the expected excess returns, which is what we want because we aren't confident about the analyst's views. So the second part of this formula is just a weighted average, combining implied equilibrium excess returns with our views. The first part of the formula is there just to ensure that the weights that we assign to the implied excess returns and to our views add up to 1. That's all that's going on here. This first term is focused solely on making sure the weights add up to 1. What is this formula then for expected excess returns? It really is just a weighted average. It's the weighted average of our implied equilibrium excess returns. It's a weighted average of the implied equilibrium excess returns, which is the market's best guess of what's going to happen in the future, and our views about the future. This formula may still seem pretty worrying and very complicated. Let's work through an example. And we're going to consider just one stock, Amazon. And we calculated the implied excess returns to be 0.74% per month. And we know that the variance of returns is 2.015% squared. We predict excess returns of 2% per month, and the uncertainty surrounding this view is reflected by a variance of 0.5% squared. We can assume that tau is equal to 1 and p is also equal to 1. Can we use the formula developed by Litterman to calculate the expected excess returns for Amazon? So remember what that formula is. We have the expected excess returns are going to be equal to tau s inverse plus p transpose omega times by omega inverse times by p, close the brackets, to the power minus 1, all multiplied by the inverse of tau s times by pi, which is our implied equilibrium excess returns, plus p transpose times by omega inverse times by q, where q represents our views. Let's plug the numbers into this formula. We're going to get expected excess returns are going to be equal to tau is equal to 1, so we can ignore it. S is going to be equal to the variance in this case because there's only one stock. We know that P is equal to 1. We know that omega is equal to 0.5 because that's the uncertainty. And we know that pi is equal to 0.74 and Q is equal to 2. If we fill those numbers into the formula, we're going to get 0.02015 to the power minus 1 plus 0.005 to the power minus 1, and all of that is to the power minus 1, multiplied by 0.02015 to the power minus 1, times by the implied equilibrium excess return, which is 0.0074, plus 0.005 to the power minus 1, times by our view, which is 0.02. Close brackets. And if we do the calculations here, we're going to get, open brackets, we're going to get 49.63. That's what we get if we do 0.02015 to the power minus 1 plus 200. That's the value of 0.005 to the power minus 1. And that's all going to be taken to the power of minus 1. And we multiply by 49.63 times by 0.0074 plus 200 times by 0.02, which is going to be equal to 249.63 to the power minus 1 times by 0.3673 plus 4. And we can rewrite this now as 4.3673 divided by 249.63, because remember 249.63 to the power minus 1 is just equal to 1 divided by 249.63. And that gives us a value of 0.0179495, which is equal to 1.749% per month. That is our estimate of expected excess returns for Amazon. Does this estimate make sense? Is it consistent with our intuition? The implied excess returns are 0.74% per month, and the variance or the uncertainty surrounding that is 2% squared. Our own views are that the excess returns will be 2% per month, and the uncertainty surrounding that is just 0.5% squared. So we are much more confident about our views relative to the market. In our formula, that means we're going to place more weight or more confidence on our views. So we should see that the expected excess returns are going to be dragged up towards our views of 2% per month, because we're very confident about our views. And that's what we see. The expected excess returns are indeed pushed up towards 2. We get a value of 1.749% per month, because we're very confident about our views. If we were less confident about our views, suppose the variance was equal to 2%, then the expected excess returns would be lower. And you can try this to make sure that it's working. And you can try this to make sure that you can apply the formula. If you're having difficulties when you change the value for the uncertainty surrounding the view, let me know. Please come and see me. Hopefully this example has demystified the formula to some extent. In reality though, we don't just deal with one stock. We deal with lots of stocks. Here's a more complicated example, and we're going to go back to our 5 stocks that we've seen throughout the course: Intel, AEP, Amazon, Merck and ExxonMobil. And we have calculated expected excess returns using historical data and the CAPM. We also calculated the implied equilibrium excess returns. That's the values that are represented here in the table. Now suppose we want to combine the implied equilibrium excess returns with our views about these stocks. How do we do this? Well, consider our views. We have 2 views. First of all, analysts tell you that AEP has found a way to store electricity. Based on this breakthrough, they expect AEP to outperform ExxonMobil by 1% per month. The second view is that given the current economic conditions, we think that Intel will outperform Amazon by 1.75% per month. The views expressed above are relative views of assets. We are taking a view of Intel relative to Amazon. We're taking a view of AEP relative to ExxonMobil. Relative views are very common in reality. Typically, analysts will look at underperformance or outperformance relative to another stock or asset. Absolute views, such as AEP having returns of 2% per month, are much less common. So we're not going to deal with absolute views since they're really not used much by industry practitioners. How do our views match up to the implied excess returns? AEP has implied excess returns equal to 0.0032 or 0.3% per month, while ExxonMobil has implied equilibrium excess returns of 0.6% per month. The difference in the implied excess returns between AEP and ExxonMobil is negative 0.32% per month. In other words, according to the implied excess returns, ExxonMobil will be outperforming AEP. But our view is that AEP is going to outperform ExxonMobil by 1% a month. So what would we expect to happen if we incorporate our view? Well, we would expect to see the excess returns. Well, we would hope that the expected excess returns for AEP will be increased, while the expected excess returns for ExxonMobil may be lower. And in our portfolio, we would hope that we will hold more of AEP and less of ExxonMobil. What about the second view, that Intel is going to outperform Amazon by 1.75% per month? The implied equilibrium excess returns for Intel are 0.9% per month, while for Amazon we have implied equilibrium excess returns of 0.7% per month. In other words, Intel is expected to outperform Amazon. That's the market view. But our view is much stronger. We think the outperformance is not going to be 0.2% per month, but rather 1.75% per month. So once again, we would hope that our holdings of Intel will increase and that we will reduce our holdings of Amazon when we incorporate our views. We now have 2 views. How do we incorporate those views and combine them with our implied equilibrium excess returns? We're going to have to use a link matrix, and that matrix is called P. A matrix P is constructed in the following way. Each row of the matrix represents a view, and each column represents a company. Now in this case we have 2 views and 5 companies. So we're going to have a 2 by 5 matrix. The question is, how do we fill in this matrix? There are 2 rules about how we calculate the elements of the view matrix. First of all, relative views must sum up to 0. So the elements for each view must add up to 0 across the 5 stocks. Positive components in the view matrix for a particular view must add up to 1, while the negative components must add up to -1. That ensures that when we calculate the sum across all the stocks, it's equal to 0. Positive numbers in the view matrix show that we're positive about the company, while negative numbers show that we're negative about the company. Let's consider view 1, where we think that AEP is going to outperform ExxonMobil. What does our view say about Intel? Well, it says nothing. So we're going to enter a 0 for Intel. What does it say about Amazon and Merck? It also says nothing about those companies. It says that our view does, however, say that we're positive about AEP and negative about ExxonMobil. And we know, so we're positive about AEP, and we know that the positive components must sum up to 1. Since we're only positive about one stock, we must enter a value of 1 for AEP. Now we're negative about ExxonMobil, and we know that the negative numbers must sum up to -1. Since there's only one company we're negative about, the value must be -1 for ExxonMobil. What about our second view, that Intel is going to outperform Amazon? Here we can enter a 0 for AEP, Merck and ExxonMobil. We're positive about Intel, which means we're going to have a value of 1 for Intel. And we're negative about Amazon, so we're going to have a value of -1 for Amazon. This would be the view matrix for our example. Now suppose we had a third view. And the third view was that an equally weighted portfolio of Intel and Amazon would outperform an equally weighted portfolio of Merck and ExxonMobil by 1% per month. How would we incorporate this view? We are positive about Intel and Amazon and negative about Merck and ExxonMobil. The way we would do this is first of all think about the positive components. We're positive about 2 companies now, Intel and Amazon. We know that the positive components must add up to 1, and we have an equally weighted portfolio of Intel and Amazon. That means we're going to assign a value of 0.5 to those 2 stocks. That means the positive components add up to 1, and we have equal weights on Intel and Amazon. We're negative about Merck and ExxonMobil. Again, we have an equally weighted portfolio, and we know the negative elements must add up to -1. So we would enter -0.5 for Merck and -0.5 for ExxonMobil. We have no view about AEP, so AEP has a value of 0. This is a more complicated view, but hopefully you can see how all the rules are being applied. The positive elements add up to 1. The negative elements add up to -1. And the sum across all the views is equal to 0. Now let's think about our views and the uncertainty surrounding our views. Q is the matrix which represents our views. And effectively, when an analyst gives us some views, they're not 100% positive that their views are correct. There's a lot of uncertainty associated with people's views. It's very hard to predict the stock market. So what we get when we think about views is we get the analyst's views, but they're subject to an error term. In this case we have two views, so our matrix is a 2x1 column vector. We've got view 1, that AEP is going to outperform ExxonMobil, and we've got view 2, that Intel is going to outperform Amazon. And we have our error term. The more confident we are about our views, the smaller the error term gets. That's the key. The more confident we are about our views, the smaller the error term. If we were convinced of our views, 100% confident, there would be no error term because we can perfectly predict what's going to happen. Black and Litterman assume that the error term is normally distributed with a mean of 0 across all the stocks, with a mean of 0 across all the different views, and a variance-covariance matrix equal to omega. Omega is going to have the dimensions equal to the number of views. Suppose we have k views, then omega would be a k by k matrix. In our example, we have 2 views, so omega would be a 2 by 2 matrix. A question that both Black and Litterman have struggled with, and indeed practitioners struggle with, is how do you calculate omega? How do you get a measure of the uncertainty? There is no best way to calculate omega. It really does depend on how confident you are of your predictions. And you can adjust omega to reflect your confidence. But as a base estimate of omega, Black and Litterman recommend the following formula. Omega should be equal to tau times by P times by S times by P transpose. S, remember, is just the variance-covariance matrix for all stocks, while P is the link matrix. We're going to assume that tau is equal to 1 and we can ignore tau. In practice, if you are more confident about certain views, you can go into the omega matrix and adjust the views accordingly. This is just the base level for omega. That's all I want to talk about today. In class, we're going to talk about how you implement the Black-Litterman model in Excel, and we're going to calculate expected excess returns based on the Black-Litterman model, and then go on to calculate the portfolio weights. See you in class.